Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
Is it possible to have two suns? Would we still be alive?
Would we?
And why stop at two? Why not three, four, five, six, seven, eight?
Chill.
Fine.
To answer all of your enigmatic questions, we first need to know what gravity is.
Fair enough.
Well, gravitation or gravity is the force that pulls objects towards each other. It's
एक सेकंड ग्रेविटी कब से फोर्स बन गया? Since when did gravity become a force?
अरे यार, you wait ना भाई.
Okay.
We'll answer all of your questions.
Fine.
All of your deep questions, whatever they are.
Yeah, we will.
Just wait for some time. Yeah. So, gravity is what makes things fall to the ground when you drop them, and it is what keeps us firmly planted on Earth. Imagine you have a ball and you let it go. It doesn't just float away because, of course, the Earth's gravity pulls it down.
And gravity works on everything with mass. The more mass an object has, the stronger is its gravitational pull.
Correct.
That's why planets, stars, and moons have significant gravitational forces. Like even humans also exert gravitational forces.
Correct.
Like it's literally every single thing with mass.
Correct.
So you can think of gravity as an invisible magnet that draws objects together. This quote unquote magnet gets stronger the closer the objects are together. For example, the Earth has enough gravity to keep the moon in orbit around it, and the sun's gravity is strong enough to keep all the planets in our solar system orbiting around the sun.
Yeah. So even though we can't see gravity, we basically experience it all the time. And it's the reason why you weigh less on the moon than on the earth. Because the moon has less mass, so its gravitational pull is weaker. And gravity is also the reason why planets and stars form into spheres. The force basically pulls everything evenly towards the center.
Neat.
It is. So, in a nutshell, gravity is the force that makes things stick together, fall, and orbit. It is one of the fundamental forces that shape the universe. But coming to Arnav's point, you have to keep
Exactly.
in mind that it isn't really a force, according to Einstein. It is the mutual attraction of the two objects due to the bending or curvature of something we like to call space time.
And we'll definitely explain that in excruciating detail in another episode. Okay?
Yes.
So let's start simple for now. As we know, the moon orbits us Earth, right?
Yeah.
But that's not the right way to say it. The moon and the Earth orbit their common center of gravity. So the Earth's not sitting there. The moon's going around the Earth with their common center of gravity. The Earth's not like just stationary.
Yeah,
the Earth is also
rotating.
moving. Exactly.
That's why the Earth rotates.
Exactly. So you know it's 1,000 miles beneath the Earth's surface.
The center of gravity, right?
Yeah.
Yeah.
It's along the same line, like along the center of the Earth and the center of the moon. It's along that line.
Yeah.
So as the moon moves here and there, the center of mass line shifts.
Correct.
So the Earth's kind of like jiggling and wiggling as this moon goes around because that's how it's rotating, as we said.
Yeah.
So this is the two-body problem. And it's perfectly solved using equations of gravity and mechanics. And Isaac Newton solved it.
My bakra. Oh, just to let you know, bakra is basically Hindi for goat, which is greatest of all time, basically.
For all our non-Hindi speaking viewers.
Correct. So, well, whatever Newton did worked. And Newton also applied these equations to the Earth's moon system going around the sun. And that worked too. But for just a moment, let's ignore the moon.
Okay.
So, what we have is basically the Earth going around the sun. And this is another two body system. But then the ingenious Newton said that every time the Earth comes around the backstretch and Jupiter's out there far, far away in its own orbit, Jupiter exerts a tug on the Earth a little bit. I mean, it has a lot of gravity, but since it's so far away, the tug isn't that much, but it is significant enough to notice.
Yeah. But why is it like so less that you would ask? Because
Yeah.
the gravitational attraction of an object, it depends both on its mass and the distance between the objects. So the more the distance, the lesser the gravitational force.
Correct.
And more the mass, more the gravitational force, as we said earlier. So again and again, Jupiter will tug on Earth as Earth comes back around to the other side. And since both of them are in the same direction around the sun, Earth will have to go a little farther in its orbit to be aligned again with Jupiter, but Jupiter is still going to tug on the Earth.
Now, Newton looked at these tugs and he got cold feet. He was worried that the solar system would go unstable because Jupiter keeps tugging on Earth.
And we're just disregarding the other planets now because that just makes matters way worse.
Yeah, it becomes too complicated. So, Jupiter just keeps pulling Earth away, and the previously stable orbit would just decay into chaos.
And we'll all die.
Yeah, and this is what essentially he was worried about. He even said that I know my stuff works and it looks stable to me, so it is clearly stable, even though it looks like it won't be stable. And I think every now and then, God fixes things.
Did he actually give God as his answer?
Yeah, Isaac Newton, bro, he actually gave God as his answer. He couldn't explain it.
When in doubt, just let God figure it out.
Yeah,
As if he gave up and said, I'm out.
out, definitely.
Okay. So he said just God did it and left. So now clearly we're all still here and we haven't been yanked out of the orbit by Jupiter, right? At
Yeah.
least for now. But Jupiter's pulling on us. So it's a so-called God correction. But this is the first hint that a third body is messing with you in some way. And that's a little harder to understand. Fast forward 113 years, we get to Laplace. The same guy who made the Laplace transformations.
Yes.
And he studied this problem and he developed a new branch of calculus called perturbation theory.
And this was completely unknown to Newton, even though Newton had invented calculus. Basically, Newton could have solved it. He could have said that in order to solve this problem, let me just invent some more new calculus. It's totally normal. But of course, bro didn't do it.
So Laplace developed perturbation theory, and in this case, we're only discussing about two bodies, the sun and the earth.
Yeah.
There's a third one, the tug is small, but it's not irrelevant because it's there and it's periodically repeating. So the earth and the sun, like we're talking about Jupiter, right?
Yeah.
It's way out there, like it's like almost halfway of Pluto.
Yeah, quite far away.
Yeah, so it's like a very small tug, so you can run the equations in such a way that a two-body system that is tugged very often by something small cancels out in the end.
Yeah. So when it's out there and the tug is a little bit, but
But
now
if
it's
that way over the here, then the tug is less.
Yeah.
Then some tugging you in this direction versus that direction, and like all that configuration,
yeah.
it all adds up and it all cancels out. And Newton could not have known that without perturbation theory.
Yeah. So that took care of the third body basically, where our solar system is basically stable for the foreseeable future in ways that Newton had not imagined. And for that, Newton required God, but Laplace did not. So let's say that we have not just a planet, but and one of its moons, and say another star and one more star. So a double star system.
Oh yeah, this was in Star Wars.
Yeah, Star Wars: A New Hope. Yeah, I think it was 1977. I think.
Yeah, you all can watch it.
Yeah. So orbiting 2 or 3 or 4 suns, so that those 2 suns and the planet is basically stable.
So here's the interesting part. If you take the third sun, so this was a double like sun system,
Yeah,
kind of like
yeah.
double star system.
Correct.
If you put a third sun, and if it's like around the same size, so like three identical suns,
Huh.
then what kind of orbits will they have? Because where will their gravitational allegiances go?
Yeah.
One planet, like this is one planet where the Star Wars planet. The planet is saying, am I going to like go here, there, whatever? Am I going to go towards this sun, that sun? Like,
Yeah,
what are
because
they going to do?
you don't know if they're like almost the same mass. Is it going to go around one sun or the other sun? So that is technically not decided, right?
Yeah, and it's like basically, it turns out the orbits of a three-body problem are mathematically chaotic. So it does go around somewhere, right? It doesn't like, and eventually it may crash also, but it's mathematically chaotic.
Yeah, so that was extremely random. And something has to give way. Otherwise, they will collide and maybe one or more of the stars could get ejected. So, this is the classical three body problem, and three objects of approximately a similar mass are trying to maintain a stable orbit. But as to the knowledge that we have now, this cannot happen and it goes chaotic even with just three objects.
So supposedly it's an unsolvable problem.
Yeah.
Personally, I don't believe it, but you can calculate incrementally what's happening and track it until the system dies or splits apart or whatever, like until it ends. But you cannot analytically predict the future of the three-body system. But one second, why can't we?
Because what chaos will do for you in your mathematical model is that if you change the initial conditions, say even by a little bit, like a teeny tiny bit, the solution will diverge so much that it goes crazy. And it's not just a little bit different, but it is exponentially different with even the smallest increment of any kind of distance.
Oh yeah, actually I watched I saw a YouTube video where they model the distance of Mercury from the sun,
Yeah,
and if they change the distance by even 1 millimeter,
yeah.
that led to like the whole solar system going astray and like collapsing.
Oh,
That's like that's how that shows the
yeah.
scale. So to overcome this insanity, there's something called the restricted three body problem, and that is basically you got your two bodies of approximately the same mass, but now the third body is small. So the two bigger masses will orbit each other like close orbits,
Yeah.
and the small mass will act as if those two bigger masses are one huge mass and will orbit around them like throughout, like both. So basically, finally, that's a restricted three body problem where we have two masses that are approximately equal and one that's much less than the other two.
And this is solvable. And this is the same case as in the Star Wars movie as well, because you
Yeah.
have two stars and then you have the little planet, and it's even better because the planet is like so far away that it feels that the two stars have like a merged center of gravity,
Yeah.
basically, and they're orbiting each other. They're orbiting the two stars just like any normal body that orbits it, and they're far away. So that difference is not really mattering to the tiny planet that is far away, and it maintains a stable orbit around both the stars.
So it's like definitely possible to live in those
Yeah,
conditions.
correct. So now if it got really close, then you'll have some issues, because then again gravitational allegiance will come into play, and where the planet is like, hey, who do I get attracted by? And the stars are not going to care, and the planet doesn't know where to go.
Exactly. So now, anyways, the most supposed takeaway here is that it's unsolvable.
Correct.
Now, this is probably not just because we don't know how to do it yet, but because it's mathematically built into the system is chaotic, literally. And unless you can make certain assumptions about the system that you'd invoke, like you can solve them, like one is a small object and the other ones are bigger and all that, then unless you make those assumptions, it's not like solvable.
And by the way, even in the solution with Jupiter out there slightly tugging on the Earth, it is somewhat chaotic, but over a much longer time scale than Newton had ever imagined.
Oof.
Yeah, so sooner or later, our perfect little Milky Way isn't gonna have all its planets happy anymore.
Oh, so sad. But it's not deeper than this now. It's done.
Yeah.
Because we could have said the four body problem or the five body problem, as I was saying in the
Yeah,
start.
the nth body problem.
Yeah. But this third body problem is the beginning.
Yeah.
Because it's going to have the same thing. We're going to have the same thing in 4 or 5 bodies. It's just going to be worse because it's more stuff that you have to take
Even
into
more
consideration.
worse, correct.
But it's the same starting point for now.
Yeah. And we have star clusters with thousands of stars in them, and they're just all orbiting each other and whatnot. We can model it, but we cannot predict with precision where everybody is going to be at any given point of time, say like 100 years ahead in the future.
Or even 100 billion.
Yeah. So since it is so chaotic, the only thing we can do is just model the chaos. We say that this will be statistically the most probable way that it would look like our prediction over time, but we can't be sure.
Oh, uncertainty.
Yeah, and this is the beauty of science.